Okay, this is your introductory video lecture for Chapter 6, Intermolecular Forces, Attraction Between Particles. What are intermolecular forces? Easiest example, let's take a look at a water molecule. And in Gen Chem 1, we learned an awful lot about uh, intramolecular forces and the forces within a molecule, if you will. So we learned about these bonds here. This here is a covalent bond. This is an intramolecular force. What we're learning about in this chapter are the individual forces between the molecules. So what holds this water molecule here to this water molecule here? That's what we're studying here. These intermolecular forces, incredibly important forces because they are going to dictate for us and determine whether or not a substance is a solid, a liquid, or a gas at a given temperature. So that's why they're very important. And there's a lot of physical properties that we can predict from an understanding of intermolecular forces. So we need to point out our learning goals for this chapter. What you're going to do is to take this knowledge about intermolecular forces throughout this chapter, and you're going to apply it to understanding physical properties, things like boiling points. You're going to ultimately interpret phase diagrams, and we'll get to what those are later, and be able to explain solubility trends, for instance, for both nonpolar and polar solutes. And lastly, briefly, we'll talk about hydrogen bonding, which is a specific type of intermolecular force. So as a review, and I'm going to spend a little time here because this is important, we've got 4 different molecules. We've got carbon dioxide, we've got H2O, we've got oxygen, and we have ozone. And there's 2 questions underneath these molecules. Which molecule is polar? It contains polar bonds, so one of those 4 satisfies both those criteria. And which molecule is nonpolar despite containing polar bonds? Which means the other 2 would not have polar bonds and would therefore also not be polar. So as a review, we need to remember something about electronegativity, which is the key to understanding where polarity comes from. So imagine this being my periodic table, and the very top right element then would be fluorine. And what you remember from your trends in electronegativity, remember electronegativity increases up and over in the periodic table. So fluorine is your most electronegative element. On the Pauling scale has a value of 4.0. No other element has that high of a value. All the others are less. So fluorine is the most electronegative element. Polarity comes about by pairing atoms together that have differences in electronegativity, and you wind up with what we call a dipole. So if you pair elements together and their electronegativities are significantly different, like hydrogen and fluorine, what you wind up with is the electrons in that bond, if you will, spend more time located close to the fluorine nucleus as opposed to the hydrogen nucleus. And one way we denoted that in our, at least in my class, was to show that the electrons are pulled towards the fluorine, hence resulting in a positive tail, if you will, a positive end to the molecule on the hydrogen, and the electrons pulled towards the fluorine. Another way we notated it is like this. We said a partial positive charge and a partial negative charge. This is really a more moderate extent of electron transfer. So if you were to pair something like cesium to fluorine, because cesium's down here on the periodic table, these electronegativity differences are vastly different. And what results is what we call an ionic compound, a true ionic compound, where you have now cesium plus and fluorine negative. The electrons are completely transferred. So polar molecules, polar species, are kind of lesser degree of electron transfer, not a full charge differential as you see in something like this. Now, obviously, if we pair up atoms with the same electronegativities, they're very close. They don't have to be the exact same atoms. Some electronegativities are very close. we obviously wind up with a complete uniform sharing of those electrons, and therefore we don't wind up with any sort of dipole here. There is no dipole moment. This is a nonpolar covalent compound. This is a polar covalent compound, and this is an ionic compound. So these are the two extremes. This here, ionic and nonpolar. This is where most species exist, somewhere in between. So going back to the questions then, which molecule is polar and contains polar bonds? Okay, so right off the bat, we can say that this one here is going to be nonpolar. 2 oxygens, same electronegativity. 3 oxygens, all the same electronegativity. These cannot have polar bonds and obviously therefore cannot be polar. When we look at carbon dioxide, we talked about this when we talked about Vesper theory in Gen Chem 1. Even though these are polar bonds, electrons are pulled towards the oxygen, which is more electronegative. But since the attached atoms are identical, and this is a symmetrical molecule, that kind of tug of war cancels out. You wind up with a nonpolar despite containing polar bonds. So the answer to this one is CO2. Leaving water is the answer to the first one, which is obvious. We have oxygen pulling in this direction and this direction away from the hydrogen. You get a net dipole moment in this direction. So that is the answer to the first question. That is spending some time on a review, but it's very important. So we move forward then to our first type of intermolecular force. We're not going to talk about all of them. This is an introductory video. London dispersion forces I've chosen to talk about because I want you to start reading on this. They're a little bit abstract, and I don't want you to spend too much time killing yourself over this. But imagine 2 atoms, first of all, just 2 hydrogen atoms coming together. And when you think about the quantum mechanical effects here, we have the 2 nuclei, right? Let's say that at a given moment in time, the electron resides in a region of this particular hydrogen that is fairly close to the other hydrogen atom. In fact, maybe it's attracted to that nucleus. Then momentarily, at that time, the electron associated with this hydrogen over here is actually going to be repelled and ultimately will be, if you will, on the other region from the atom, separated from as far apart as possible as the electron from here is what I'm trying to say. So what you wind up with really is kind of a partial negative charge here. I don't want to do that. It's not really in the correct notation because it's a momentary dipole, but and a partial positive charge here. So this atom seriously has some a little bit more negative charge over here, positive over here. So you get this what's called this temporary momentary dipole. So as a result now, you can attract one hydrogen molecule to another by theoretically saying, okay, you realize you've got this kind of possibility here to attract these. So this is why they're present between all molecules, because anytime you have atoms, this can happen. And it's almost like a domino effect. If you have a large molecule, you have a summation of these London dispersion forces where all the atoms start to respond, and you wind up with what can be a fairly large force if you have a large molecule. So definitely do some reading on that. It is a little abstract. So once we start to see these intermolecular forces build up, we can actually see it manifested in physical properties. For instance, viscosity, which most of you probably know has something to do with kind of the flow of a liquid. You think of molasses as being kind of thick or doesn't flow. That's what it is. It's resistance to flow. That's what viscosity is. What we notice is that it increases with molecular size, and another factor is shape. So the idea here is if the molecule is, if the individual molecules slide past each other easily, then we could say there's low viscosity. But if they trouble to move past each other, then that's what you're doing. You're having trouble like kind of breaking these intermolecular forces. That's what the resistance of flow comes from, and you'll see that. In the very next slide, you can see what happens is viscosity. You don't worry about the units. increases as the molar mass of these compounds increase. And this is just a what we call homologous series of alkanes, hydrocarbons. And we're just increasing the number of carbons and hydrogens so the molar mass is going up. And you can see the viscosity changes tremendously. And that's one of the key things to realize here is that these intermolecular forces affect physical properties. So if we look at now interactions involving polar molecules. So let's take something very simple. Let's take water, for instance. So let's take a water molecule here, as we did before, and another one over here. And now, because there are dipoles here, we get this attraction here. Now, remember, the hydrogen has a partial positive charge on it, and the oxygen has a partial negative charge. That's why they're being attracted to each other. You could start to imagine how putting individual molecules in here and attracting, that you could actually get a scenario where you get these open spaces in the molecule. And that's one of the keys, because as water freezes, we'll see at the end of the chapter, we all know this, ice is less dense than water, and because it creates this very open structure. So this is a dipole-dipole interaction, and this is a specific example of a particularly strong dipole-dipole interaction called hydrogen bonding. Sorry. It's pretty ugly there, huh? Hydrogen bonding. And I want you to read about hydrogen bonding. Hydrogen bonding occurs only under certain cases of dipole-dipole forces. The hydrogen has to be attached to a nitrogen, oxygen, or fluorine. Any one of those, and you can have hydrogen bonding. So here you see hydrogen is attached to oxygen, therefore we can get hydrogen bonding within that molecule. It's just a strong, strong case of a intermolecular force, and specifically a dipole-dipole interaction. Here's a couple terms that I would like you to refresh your memory about from Gen Chem 1. And there's a new one that you might not have been introduced to in Gen Chem 1. I think I did in my class, but missable. What we'll notice when we get into the lecture is that we can use these intermolecular forces to make some predictions about solubility. The next thing I want to talk about is phase diagrams. This is a major section of the chapter. And these are diagrams in which we look at temperature versus pressure and what state the substance is at various temperatures and pressures. And you'll see diagrams that look kind of like this and things like this. And the easiest thing to do is just go to a phase diagram for water right here. And what you see is temperature versus pressure, and what you see is the state at which water exists at these different temperatures and pressures. If you took normal atmospheric pressure and you realize, okay, there's the freezing point of water, 0 degrees C, so anything below that, it's a solid. And of course, in this region, it's liquid, and then you get to a high enough temperature, boiling point, then it's going to be a gas. But we also notice that pressure controls whether or not a substance, to some extent, will be a solid, liquid, or gas. So at 200 degrees C, we can actually take the gas and apply enough pressure to get it to condense and form the liquid. And that's the way to interpret this graph. You can see that now, is as you change that pressure. And of course, if pressures are really low, below atmospheric pressure, you can see how we can go from solid to liquid to gas, of course, by increasing the temperature. But the temperature at which that occurs, these changes occur, will depend to a large extent on the pressure. So there's a couple things you should note as you read and you look through these your slides, is the triple point, the critical point, and the supercritical fluid on these diagrams. Here's your triple point, right there. There's your critical point, and there's a supercritical fluid. A triple point is when all three phases coexist. So basically what you have is everything going on. Water is freezing, ice is melting, water is boiling, gases are condensing. All this is happening at once. The critical point is specific temperature and pressure at which the liquid and gas phases have the same density and are indistinguishable from each other. And going above that then, above that critical point results in a supercritical fluid. Supercritical fluid have a lot of practical applications. Just to give you one example is in dry cleaning. Now you can use supercritical fluids like supercritical carbon dioxide as opposed to some of the solvents that used to be used, which are toxic and some are carcinogenic. So that's a good advance in green chemistry. Lastly, in this chapter, you'll notice some remarkable properties of water. It has to do with the fact that it has these hydrogen bonds. It's all based on this idea, really, and that is just a strong, remember, dipole-dipole interaction. But you can read about surface tension and the meniscus that forms. It has capillary action. And lastly, very important to realize that, in fact, the density of water changes with temperature. And what you'll notice is that as you get colder and colder, that density drops. The max density is at 4 degrees C, and then ultimately ice is less dense. So ice is somewhere down here. I forget what the density of ice is, but it's off of this scale, I believe. And that's critically important because when you think about natural water chemistry, if the solid was more dense than the liquid, in most substances, if you take if you freeze it, turn it to a solid, and drop it in its own liquid, it will sink. So water is unique that way. And most of your substances that have hydrogen bonding, that's what happens. That's critical for the evolution of life and for life in general. When you think about it, if a lake were to freeze and the solid was more dense than the water, what would happen? Well, the top freezes because that's where the air temperature is dropping, right? And then it would sink to the bottom. And then another layer would freeze and it would sink to the bottom. And ultimately, you'd have a big block of ice rather than a lake, which has water with a top of it frozen. So that's critically important. So come to class prepared to go over some more concepts in Chapter 6.